Hi, I had a few questions generated from our last couple of classes about column 3 and column 4, electron dot and the orbitals, how the hybridization works. So I thought I'd try to clear it up at least a little bit. So here's a little bit of discussion. In this particular slide, what do we have? We actually have I'm just getting set up here on our drawing part. So we would have a carbon here and another carbon. And remember, it forms a tetrahedron shape. So what would happen is one tetrahedron comes along, and then the other tetrahedron comes along, and you end up with a bond of 2 electrons in an orbital, and then you got 3 other sticky orbitals coming off both of those tetrahedrons. And each one of these would have something bonded onto them. Often hydrogen. You could have chlorine, and you can work out the electron dots to see that this would work. You could have these two come together to form a double bond with oxygen, where you'd have this orbital shape here and an orbital shape here sort of thing. Okay, and then you could have a hydrogen over here or chlorine. So you still have to balance everything to get to those 8 electrons. And because carbon is in that lovely 4-legged shape as such, the tetrahedron, carbon can easily get to that number 8. Whereas when we think about hydrogen, we get to the 2 because it's only filling that s orbital. Okay, so this 2-8 rule works really well in column 4. Now, when we go from our single bond to our double bond over here, it's interesting because what happens? Now we got balloon shapes here. I'm just putting electrons nearby, and you're going to end up with a bond here, which will look like an orbital space, and another one here. So now you get a double bond between your carbons, and again you have these other electrons off on the other sort of orbital toothpick things, and you can end up with hydrogens or chlorines, or then you end up with different naming depending on what's on there. Okay, and your hydrogens again are going to end up with 2 electrons, right? One from hydrogen and one from the carbon. Okay, in case I'll put those dots in case that helps you think about it. And you might notice the double bond makes those carbons get closer together. Okay, the angles aren't quite right. It was difficult to do this on a flat surface and try to take pictures. But anyway, hopefully it gives you the right idea. Now we also have triple bond. So in the case of a triple bond, what do you have? You have one bond here, you have another bond here, and one down here. Think of this triple bond where 2 electrons are being shared. Now, in order to make sure that we get all the electrons we need, you would have, what do we have for this carbon? 1, 2, 3, 4, 5, 6, 7. And you would have the same thing over here right now. So what you would need, oh, my pen left. Sorry. Here we go. I'll get that pen back. If you had hydrogen, it's your simplest one to sort of think of, then you're going to have 2 electrons here and hydrogen over here. Now, if you count up, what do you get? For this carbon, oh, come on, draw. There we go. What do you have? 1, 2, 3, 4, 5, 6, 7, 8. What do you have for the hydrogen? 2. Over here, same thing. This carbon, 1, 2, 3, 4, 5, 6 shared with the other carbon, and 7, 8 shared with hydrogen. And then this hydrogen would have 2. So this 8-2 rule works really well for column 4. And almost everything wants to get to column 8. And as you can see, whether it's a single, double, or triple bond, it's all hybridized. The s orbital that was round and the p orbitals, the pop bottle shapes, have combined into this tetrahedron shape. Okay, so it works for all single, double, and triple bonds. Okay, now I know we're kind of going backwards to have this being column 3 as such, but what do we have for aluminum? Well, aluminum is in our third, one, two, three, yes, third row. Wanted to make sure I was actually correct on that. And so what do we have? We have these layers and layers of s orbitals, and we have layers of p orbitals. And in fact, I think I'm missing an s orbital in my drawing. So, because you would have 3 of them. So that I'm off by a little bit. So what do we, oh, come on, pen. There we go. So the pen would have, you'd have one more s orbital in here. Okay, so you'd have 3 layers of s orbitals, and you would have 2 layers of p orbitals, because remember the p orbitals start in the second row. Now, what do we do? What do we care about for which electrons? We only care about the electrons in the last row. Those are the outer electrons, which are called valence electrons. So what do we have in the valence electrons? You will have 2 electrons in an s orbital, and then you will have 1 electron in the p orbitals. So what do you have in total? 3 to work with. Okay, so we'll have a look at what that looks like. Okay, so what do we have here? We have aluminum, and in aluminum, there we go, my drawing is working properly now. You have 2 outer electrons in the last s orbital, which is row 3, and then you have 1 in the 2p orbitals. And so what this matters is this thing that sort of looks like a flower. These are just the outer orbitals. They form a sort of Y shape. And you get electrons in each of the 3 sort of orbital shapes, that is s and p orbitals combined. Okay, so that gives you a Y-shaped difference. So column 3 normally forms this hybrid shape. And then you can end up with bonding. I mean, you could have a hydrogen, and then you could have another hydrogen down here and a hydrogen here. Okay, you could have instead, you could have a double bond with oxygen. Okay, or you can have a triple bond where all 3 are bonded to another Y-shaped thing, if that's not the least bit confusing. So column 3 and column 4 end up doing these hybrid shapes to be able to have these electrons available for bonding. If you think of these inner s orbitals, they're a little bit farther in compared to the shape of the p orbitals. So they combine and reconfigure into these others. That's not the critical thing to worry about. This is as far as I kind of learned the hybridization aspect. What's really key is trying to figure out the dots. Okay, trying to see what bonds to what. So we'll have a look at that in just a moment. So we kind of mentioned this already with the column 4, that you have the s orbital and then the p orbitals, and this combines to make this sort of tetrahedron shape with equal spaces apart. Remember, electrons are all negative. They want to get as far away from each other as possible. Okay, so the question was also posed to what to do with a bonding of hydrogen, carbon, and oxygen. You would actually have to do this as an ion because you can have different combinations, but an example in this case is what we just did, H3COH. Okay, so 3 hydrogens, a carbon bonded onto an oxygen, and then bonded onto another hydrogen. So what can happen though is you can have these separate in water and get ions. It's kind of like when you think of table salt. is sodium and chlorine. And when they dissolve in the water, you get sodium positive because it loses an electron to chlorine negative, which gains an electron. So sodium is still happy because you can either have that the s orbital is filled with 2 or it's lost the 2 entirely. It's a whole other aspect of it. And then chlorine has gained and it's gotten all the orbitals filled with electrons. So we get the same thing that you've got ions that when you put some compound in water, depending on if it dissolves, you can end up with ions floating around in the water. So what happens is you can't have just HCO. The electron number does not balance out. But you can have HCO positive, which means it has one more proton than the number of electrons. So it means we have to remove an electron. So when I started playing with this myself, because when I did the electron dot originally, I set up the 4 dots for the 4 outer electrons for carbon, and I set up a hydrogen over here. And I'm kind of used to also sort of thinking it's a little higher level perhaps. Oxygen has 6 dots for 6 outer electrons, column 6 again. You can do this double bonding. Okay, so I saw it this way. You could have, and I would think some of it could get set up this way, and you end up losing one of these electrons to make it positive. You can't have an electron hanging out by itself. Okay, now to make it even more balanced, when I looked it up to make it a little bit nicer, it works nicer because when you add up the numbers around carbon, what do you get? 6 outer electrons. That's not so perfect. We want to get to 8. So what happens to get to that 8? Carbon actually forms a triple bond with oxygen, and then oxygen has one lone pair by itself, and one electron gets removed. So this triple bonding. Now this is a much more complicated electron configuration.